All right, everyone. Today is the first lecture of Chapter 8, where we apply stochastic calculus to questions in mathematical finance. Okay, so what I'm going to do today is really just review the basic concept we need from math finance and give them some probability meaning. Okay, so what we're going to work with always is what we call a market model. So the simplest case of a market model is when you have only one risky asset, and think of this as a stock, it could be a bond, it could be a currency, it could be many things, okay? And we model this asset by some stochastic process, ST. For us, this stochastic process will be an Ito process. And it has some filtration. This filtration, think of it as the inflammation of the stock as time goes by. Okay? So one risky asset. We could complicate things that have many risky assets, but let's start with one. And then what we have a risk-free interest rate. So think of it as the rate in the money market. And that is also, in general, modeled by stochastic processes, RT, right? Okay, so with this interest rate, we have a risk-free asset. So think of it as putting your money in the money market with the risk-free interest rate. So now the risk-free asset, we know how it grows if I know the interest rate, and that's just the usual exponential differential. That is the variation in AT, so that's the risk-free asset, is just proportional, and the proportion is given by the interest rate, proportional to the value of the asset at time t dt. Okay, so that's an equation you can solve, even though RT might be random. Okay, because that's the exponential, and if you think about it, this is the solution. AT is given by A0 times the exponential of the integral from 0 to t, or as ds. Okay, even though R is random, you can solve this. Okay, that's not a problem. Take the derivative of that. If I take the derivative, then what I'm going to get is AT, because that's an exponential, and the derivative of the integral is just what's inside RT. Okay. All right, so usually we won't work with the risk-free asset per se, but we're going to work with the discounting process. And the discounting process, what is it? So I write it dt. The discounting process is just the inverse, okay, of the risk-free asset. So dt is equal to AT inverse, or this if you want, okay? And therefore, if I actually take the differential, it's not hard to check that how the discounting process evolves is just minus RT dt, okay? So that's the discounting process. Now, what's the meaning of the discounting process? It's it adjust the value of money over time, okay? So if I have $1 today, then a year from now, the dollar, because of interest rate inflation, might not be of the same value, okay? So $1 today will buy me some stuff, and $1 in a year might buy me more stuff, okay? So we have to account for that, and that's the difference. I mean, that's something that is really a math finance concept. And so what's the meaning of dt is to adjust or discount the value of future dollar at time t in terms of dollar at time 0, okay? So that's what I mean here. So you want to express the value of the asset in the same unit, even though they might be at different times. So you actually pull back everything at time 0, dollars at time 0. That's the meaning of the discounting process. Okay, so that's a market model. So what do we have here? We have the risky asset, the risk-free rate, and the discounting process as defined through the risk-free rate. Okay, the simplest example maybe of that, non-trivial example, is the Black-Scholes model that you've seen probably before. And so in the simplest Black-Scholes model, what we take for the risk-free, the risky asset, is a geometric Brownian motion, but not necessarily a martingale, right? Because I have mu here, so it's a geometric Brownian motion. And we know how to write the SDE of that. Just apply Ito's formula. We did that example, and that's the SDE. Okay? Now, in the case where mu is equal to sigma square over 2 minus sigma square over 2, then I have a martingale. But in general, I might not. That's the SDE. And the risk-free rate, we just simply take it constant. RT is equal to R. Okay, so the discounting process is really simple. Here's e to the minus RT. Okay? Great. So that's the Black-Scholes model. Now, what's the goal in this section is to be able to price derivative. What is a derivative? So here's the grown-up version of what a derivative is. So derivative security for the market model is a process that we write OT for option from 0 to big T, which is the expiration or the maturity. That is adapted. That's the key point. Okay, usually adapted, we kind of, okay, it's of course adapted. But here it has to be adapted to the filtration FT. Okay, so FT, remember, is the filtration of the risky asset. Okay, so I know the information of the risky asset. So what does it mean to be adapted? That means that it's measurable at every time, measurable with respect to FT. So that means the price, OT, the value of price at time T is determined by the process, ST. Okay, so that's why we call it derivative. If the price is derived from another security, okay, another asset. Okay, so that's the key sentence. So it's derivative, it's adapted to the filtration of another asset, and therefore it's determined by it. Okay. All right, so here's some classical example of derivative. So now from a derivative, we have the payoff. So what's the payoff? The payoff is the value at maturity or expiration. And so therefore it's O big T. Okay, so the first derivative we see is a European call option. We write C for call. So what's the payoff? It's the maximum between 0 and ST minus K. So the price of the risky asset at expiration minus K and 0. Okay, so it's the positive part of ST minus K. K is called the strike price. So what is the financial meaning of this? Is that at expiration, if I own an option, if ST is bigger than K, then I have a positive value for my option. And if the ST is smaller than K, then the value is 0. So if you think about this, this means that this asset, this derivative, gives you the option of buying at the price K, the asset at expiration. Now, if at expiration the price is smaller than K, there's no point of exercising this option. This option is useless, so it has value 0. However, if ST is bigger than K, of course it is very valuable to own an option, and the value of it is just buying at K and selling at a ST, right? So ST minus K. So that's a call option. What is a European put option? It's a bit kind of the opposite bet. It's the option of selling the asset at a strike price K at expiration date T. Okay, so of course, if ST, the asset has a price which is bigger than K, I will not exercise the option. I will just sell it at the given price of the market. So this option has value 0. Okay, and if K is bigger than ST, it's valuable to sell at K, at price K. So this is the value of my option. All right, so there's also the forward contract. So a forward contract is has value ST minus K. Okay, so what's the financial meaning of this is that at time T, if you own a forward, you're going to sell at price K the asset no matter what. Okay, so you might lose money on this. Okay, so for options, it seems that you never lose money, but of course, this option has a price. Okay, well, as we will see, we're going to price this option. So this value has a price, and therefore, there's no free money. So what's the problem here? Again, I say what a derivative here. So what's our goal? We know the payoff of this option. What I want to know is derive a formula or an expression for the price of OT at every time T. That's the problem that we're interested in. That's what I'm saying here. The problem we're facing is to deduce OT for all time T. If we only know the payoff, which seems ludicrous, however, we can do that with additional assumptions. Okay? And those are assumptions that come from math finance. Okay. All right, so for we're going to see many other kind of options. We're going to see options whose payoff is simply a function g of st, so it's a generalization of the above. Here the function is just s big T minus k, and here the function is the positive value of st minus k, or the positive part of k minus st. All right, so more generally, I could look at a payoff which is a function of the price at expiration. And there are also exotic options, so those are called European type option. There are also different type of options, for example, Asian and look back, they're called exotic, where now the payoff is not a function of the last price, but for Asian it's a function of the average price over time. And for look back, it's the function of the maximum price you see on the time interval. Okay, so sky's the limit in terms of different derivative you can create. Okay, so let's go back to our problem. So the problem we're facing is how can I find OT at every time T if I only know the last value? So we need two values, so two assumptions. So first of all, that the options can be replicated. Okay, what does that mean? Is that using, so there was a mistake in the notes here, using the two assets in my market, that is the risk-free asset and the risky asset, I can write at every time T the value of the option as a portfolio that needs a linear combination of the risky asset and the risk-free asset. Okay, with some. So what is little at and little bt? They are just the number of units you own in every asset. They can change over time and they can be random. Okay. When they change over time, we say that there's some dynamic hedging. That means to recreate or replicate, as we say, the value of the option every time T. I have to change AT and BT as time goes by. I have to change my portfolio as time goes by. Okay? Now, the other value, the other assumption we're going to see is that the market has no arbitrage. Okay, so an arbitrage is a linear combination of assets or portfolio for which you can make money no matter what. So it costs you nothing, but there's some time tau where it's always positive at tau with probability 1, and with some probability, there's some outcome where you actually make money. Okay, so essentially this means you make money at no cost. Okay, now those that mod finance assumption, turns out that they have some more probabilistic meaning, and that's the content of the fundamental theorem of asset pricing that I might discuss at the end. Okay, so now we'll just take these as granted and then just try to price things. Okay, for those who are interested, the market has no arbitrage. That is turns out equivalent to the existence of a risk-neutral probability, and the fact that the options can be replicated are related to the fact that this risk-neutral probability is unique. All right. Okay. So that said, let's put that aside. Now, we're also gonna, so there's another assumption that I should add that is not in the notes, is we need the self-financing condition, okay? So the self-financing condition is the fact that the variation of price in your, of your option is not due to the change in the portfolio, but simply in a small time is due to the change of value in the risky asset, risk-free asset, or the risky asset. Okay, so that's the self-financing condition. Now, together with the replication condition, this gives us a nice formula that I'm going to use a lot. So let me derive that. So note that from this, I get that little at is what? I'm just doing OT minus BT, I'm just solving, times AT minus 1. Now remember that the risk-free asset is really the inverse of the discounting process. So let's use that, so I can simply write this as the discounted value of that. Now let's put that back in, the self-financing. Then I get that DOT is equal to DT OT minus BTST DAT. Now DAT I can write as well differently. I can write as, so DAT I know what it is, it's RT AT dt, which is simply RT dt minus 1 dt. All right, so let's put that, and you'll see some simplification. So DOT is equal to BTST, DST, let's do that, plus, and now look at the cancellation. So this cancel that, so plus RT OT minus BTST dt. Okay, so it turns out that you can just remember this one, and I'll explain how to remember it. So that's going to be useful when we derive prices. So what this says is the variation of OT is due to what? Well, due to I own BT stock, right? So the number of units or shares in the risky asset. So the variation of the value of my option is due to how many shares I I own in the replicated portfolio times the variation of the risky asset. So the number of shares in the risky asset, sorry. And what do I do with the rest of the money? So I own OT, so that's the value of the option, minus whatever I put in the stock. So the rest of the money, if you want, I put in a risk-free asset, which grows at this interest rate. Okay, so what this says is the variation in my portfolio is the variation due to the risky asset times the number of shares I own, plus the rest of the money that I put in the risk-free asset that grows at the interest rate RT. Okay, so that's the equation that we're going to use to actually derive the value of OT. Okay, so all right, so now how are we going to do this? Well, there's two ways to actually, we'll see two ways to price option. So price option, there's two ways. One is using PDEs, and we're going to do that for Black-Scholes first. And then the second one is using risk-neutral pricing, using the risk-neutral probability. And that's where we're going to see Girzanov theorem, which is the last big theorem in probability we're going to see. Okay? These two things are equivalent for most options, but it turns out that for exotic options, it's hard to actually find a PDE sometimes. So this is much more general if you have a strange model, okay, in your market model. All right, so that concludes the introduction to Chapter 8, and thank you for listening.